Miss Kingsbury here. Today we're going to work on a new method of solving these systems algebraically, and this is called the elimination method. It turns out if you set these equations up like the ones that you see on the news sheet, you can actually add the equations together, and what this will do is it will eliminate either the x variable, allowing you to solve for y, or sometimes the y variable will get eliminated so that you can solve for x. It's still a system of equations. We could still take the equation, solve for y equals, and we could graph these things to find our point of intersection. But this allows us to sometimes very quickly find that solution without the graph paper, without all the extra algebra. So, to begin, you will notice that these types of systems already have the constant terms lined up at the end, the equal signs are lined up, the y terms are lined up, and the x terms are lined up. So, what you can do is simply draw a line, and you can add the two equations together. Now this one's set up perfectly. If you notice, negative 3x will be added to positive 3x, and that is going to give us 0 x's. That's a good thing for using this method. Cross it out. In the middle, you will see you have negative 2y to add to positive 4y, and of course that gives you 2y. The constant terms also get added, so negative 3 plus 15 is 12. So by adding the two linear equations together, you see that we have created an equation that is super simple to solve. All you need to do is divide by 2 on both sides, and you will have your y value, which, remember, that's half of your solution. Your solution normally, if you're graphing, is going to be that point where the two lines cross each other, and we know half of where that point exists if we were to graph. So now if you remember, the substitution method had us substituting in the beginning, and then we did a second substitution. This is actually going to involve a little bit of substitution as well. So once again, I like it if you draw the arrow saying, okay, I'm taking this value that I now know, y equals 6, and you can plug it into the top equation, or what I recommend is you pick the equation that doesn't have so many negatives. This top equation has a negative term here, another negative term here, and another negative term here. And sometimes we can make silly mistakes when there's tons of negatives. So it really doesn't matter which equation you choose, but I always like to choose the smart one where I know there's less chance of making an error. So if I know that 3 times x plus 4 times y equals 15, and I now know that y equals 6, we're going to substitute y with 6. We're going to bring down everything else. We're going to clean it up, and we're going to solve for x. Being very careful to keep everything where it belongs. I think I made that a 25. It's supposed to be a 24. So let's see. I'm pretty sure that is supposed to be a negative 9. And then, of course, divide by 3. So x has the value of negative 3. And, of course, we found the y value earlier to be 6. Now, this is our solution. Remember, it's written in ordered pairs, the x value, then the y value, because it really is a point of intersection if we take the time to solve this for y equals and graph, solve this for y equals graph, and, of course, all the work that comes along with graphing is sometimes cumbersome. We want to be sure, however, that this is the correct solution. So once again, you will always do a written check. Written checks are always the same. We copy the original equation. We sub in the values that we found. We found x is supposed to be negative 3, y is supposed to be 6. So if we follow order of operations, negative times negative, negative times positive, and we finish up doing a little more arithmetic, we agree that that equation balances out with those x and y values only. Now this is only half of a check. The other part of the check is the other equation. We need to make sure that this one also works. If a point works in one equation and not the other, it's not the solution to the system. A system just means we have more than one restraint or stipulation that we're trying to solve for. So let's see, this one, you get negative 9, you get 24. Negative 9 plus 24 is definitely 15. So this would be your POI. We don't always write out the sentence, hey, this is your POI. Most of the time we say this is the solution to our system. All right, so moving on, example 2. You will see that it is set up like the other one with the x terms, the y terms, even the equal sign and the constant terms are lined up. So this makes it a great candidate for elimination method. And if you look carefully, getting ready to add the two equations together, we don't cancel out our x terms this time. 3x's plus 2x's is giving us 5x's. So you may think there's an issue here, but if you had looked at the y terms, you will see this negative 2y, when added to the positive 2y, this is your variable that cancels out this time. So remember, you're adding the two equations together, and one of the two variables will be eliminated in this method. So in this case, the y was eliminated, and this allows us to work on our constant terms and to solve for x first. So again, this is half of your solution. Your solution has to have an x coordinate and a y coordinate. So again, once you have half of your answer, it's just a matter of substituting to get the other half. So once again, we could use the top equation or the bottom. I'm going to stick with the bottom equation because you can see how every term is positive. I'm less likely to make an error with positive values. What I'm doing now is I'm making sure that the x in the equation is being replaced with the value of x that we solved for already. So that means 2 times 3 plus 2 times y should be 14. And if we do this correctly, I think we're going to get y equals 4. The only way to make sure is to once again check. You're going to check in both equations, guys, not just one equation. That one worked. And 2x's plus 2y's should be 14. And it works. Now, you're probably saying this is way too simple. It can't all be this easy. Well, you're kind of right. In this situation, when you add your x terms together, you're going to get 6x, so they don't eliminate. When you add your y terms together, you're going to end up with a negative 1y. So when nothing eliminates, we do have a slight issue. But here's the good thing. If we choose one of our variables to eliminate, you are allowed to multiply one of the equations by any value you want. So let's look closely at our y values here. If I knew I wanted to use this elimination method and I had a negative 2y on the top, I would certainly want a positive 2y on the bottom. So if you would like a positive 2y, that means you're going to have to double what's written down here in this equation. Doubling this equation doesn't change it, it just makes it look different, similar to when you have a fraction like 1/2. If I double the bottom and the top, it just looks like a bigger fraction, even though it has the same exact value. That's precisely what we're doing when we multiply one of the equations by a value. So I'm going to suggest that we work on eliminating the y's. It's perfectly set up because we already have one value that's negative. We just need this one to be twice as big. So here's the best way that you're going to use to show that you're doubling the whole equation. You're going to put square brackets around the whole thing, and you're going to show that you are multiplying it by 2. Now, if you remember distributive property, it looks a little different than this, but you drew arrows. So by drawing the arrows, you're remembering that every value in that bottom equation has to get doubled. So 3x's doubled is 6x's. My y term doubled is 2y's. And my constant term of 10 has to become 20. If you don't double everything in here, it won't work out. It means you're dealing with a different value. Just the same as if I had a fraction 1/2 and I only doubled the numerator, it would turn into 2 halves. 2 halves does not have the same value as 1/2. So that's why in a fraction you have to double both the numerator and the denominator to keep the value the same. In an equation you have to double everything to keep the value the same. So guys, we have what we want on the bottom equation. I'm just going to have you bring over the top equation so they're nicely lined up. Be careful that you don't lose any negatives. And then we're going to add 3x's plus 6x's gave us a lot more x's, but that's okay because negative 2y is going to add to the 2y and it's going to eliminate like we want it to. Remember, this is called the elimination method. Negative 2 plus 20 is 18, and this becomes a very simple equation to solve. There's half my answer. I know x equals 2. So let's see. The way I set this up, it's going to look a little weird. Let's do our substituting over here. Again, we could choose the top equation to plug into, but there's a bunch of negatives. So it turns out the bottom equation is the one I personally like. So 3 times the value of x plus y has to equal 10. 3 times 2 is 6. So if we solve correctly, y equals 4 again. So let's start checking. We are checking to make sure 3x's minus 2y's equals negative 2. 3x's minus 2y's is going to work. And let's see, we checked the top equation, so we need to grab the bottom. Guys, always go back to the original equation. Don't go to the equation that you already monkeyed with. 3 times 2 plus y, 6 plus 4. It works. So we have our solutions. Remember, these are systems that we've been working on the last few weeks. All systems can be solved graphically. We could get the graph paper out. We could do some algebra to solve these for y equals. We could see that they actually cross at negative 3, 6. Okay, but this method, remember, is sometimes quicker and easier. You don't have to worry about a straight edge. You don't have to worry about having graph paper. And they're already lined up, you know, so why do the extra algebra if you don't have to? Now, I do want to mention something about this equation right here. I rewrote it on line paper so we could talk about it a little bit differently. You can just turn your note sheet over if you'd like, and you could rewrite it on the back. What if you notice the x terms? You have a 3x on top. Wouldn't it be great to have just a negative 3x on the bottom? If you wanted to take this route, what you could do is you could, instead of doubling the bottom equation like we did so that we could cancel out the y's, you could multiply by negative 1. And again, make sure you distribute all the way through. This would be negative 3x, negative y, and negative 10. So you're not dealing with numbers that are as large. But look what it's going to do for you. I'm just going to bring the top equation over. We're not going to be eliminating the y terms right now. But as you can see, you've set yourself up so that you can eliminate your x's. That 3x is going to add to negative 3x and cancel. This is going to give you negative 3y's, negative 12. And then remember before when we solved, we had y equals 4. It's just a slightly different way of working through it. So understand that each system that you look at, you will most likely have to multiply by something. And the best thing to do is to get thinking about what you wish you had. Negative 2y wants a positive 2y. Positive 3x wants a negative 3x. And if you do that, you'll get very good at these. It's going to take a little bit of practice. But once again, just remember your steps. You're adding the equations together. Making sure that they're all lined up is a great way to tell that you should use the elimination method. And then once you have half your answer, make sure you plug it in to get the other half of your answer. All these systems, the solution is considered the point of intersection. As always, let me know if you have questions. I'm more than happy to